Okay, so I think we better start. So thanks for being here for the afternoon session of the first day. The first lecture that we're going to have now is by Theodore Papamarkou, who is a reader here at the University of Manchester, and he's going to give us an insight on topological deep learning.
I'll give it a minute. Let's start. Hello everyone, and thank you for showing up today. Perhaps before I start with my talk, it might be helpful to give you a little bit of background about my research interests. In a sense, it is even odd for me to find myself giving talks lately on topological deep learning, meaning that initially my long-standing research interest has been mainly Bayesian inference and Bayesian deep learning. At the same time, I've had an interest in graph neural networks and topology, but I never prioritized doing that work just because of my main interest in Bayesian deep learning. However, that changed when a close person, actually a friend of mine, academic friend of mine, introduced me to a group of people working on topological deep learning. This happened 2 years ago. We started meeting online, and actually it was a very unique experience for me, in the sense that the only case in the past that I had worked in big teams, usually consortia, were biomedical teams. I've never experienced before working with a team of 14 people consisting of mathematicians and computer scientists. So from that point of view, it was a unique experience for pretty much everyone involved. So this is the team of co-authors. You may recognize some names coming from different research backgrounds. So let me first give you the structure of my talk. I'm going first to explain what we mean by geometric and topological deep learning. And then I'm going to spend a good deal of time talking about higher order relations, which is a key concept for topological deep learning. So this third point in the list, higher order relations, is going to take up a good part of my time, and it will have a kind of lecture element, or better say review element. And then I will move on to combinatorial complexes, which is part of the work that our team has done. And essentially this is a new topological domain, which is an enriched domain, generalizes existing structures. And then I'm going to talk a little bit about how we can use combinatorial complexes to perform deep learning, how essentially we can define deep neural network architectures upon combinatorial complexes. And I will conclude with some demonstrations, empirical findings, that corroborate the utility more broadly of topological deep learning, but also of this specific class of CCNNs, that is combinatorial complex neural networks. So, as some of you may know, in case you have worked in the field, perhaps the seminal paper that initiated or established the term geometric deep learning is a paper that appeared for the first time in 2021, and you may also recognize some of the names involved. For example, Michael Bronstein and Petar Veliskovich from Oxford and DeepMind have been working in the area. So, in their paper, the way they chose to summarize and frame geometric deep learning is in terms of the 5 Gs: grids, groups, graphs, geodesics, and gauges. And what I've tried to do in this visualization, in this bipartite graph, is to link these 5 Gs from the geometric deep learning paper to different areas of mathematics where the concepts appear. And the reason I want to present this slide is to convey essentially that geometric deep learning is a cross-disciplinary field that spans various areas, primarily, I would say, graph theory, but also algebra, geometry, and topology. In fact, if you try to scan the literature, you will find out that geometric deep learning emerged from graph neural networks. I think it would be fair to say that the explosion in the area first occurred in terms of graph neural networks, and then we had ways of enriching graphs and performing deep learning on top of them. This slide is some sort of conceptual timeline, and it is by no means a generalization or collective timeline of deep learning. Notably, attention and transformers are not included here. I just try to cherry pick areas that have led sequentially towards the development of topological deep learning. So starting initial from neural networks about half a century ago now, moving on to convolutional neural networks, then the explosion of graph neural networks came. I think it's been more than 5 years that there is an exponential growth now in papers in the field. And in fact, you may have also noticed that there is nowadays a dedicated conference for graph neural networks. It's called MLOG, Machine Learning on Graphs. And I think this is a result of coordinated effort by PMLR and perhaps arose out of workshops in major conferences focused on graph neural networks, which demonstrated that indeed there is a lot of research activity in the field. As I mentioned already, then geometric deep learning appeared, and we're just putting forward the term topological deep learning, which is obviously the context of today's talk, and we'll have time to elaborate on what we mean by this term. So the next few slides will try to motivate why topology is actually important in the context of statistical learning, let's say broadly, and in the context of deep learning more specifically. So in this first slide, what I'm trying to say is that there are specific setups, research problems, where data are supported on higher order domains. And I'm giving 3 specific visualizations examples. On the left-hand side, you can see an edge-based vector field. So essentially, you can think of a scenario where the edges, which are visualized by these arrows, are populated with data. We will mention some examples of where this can happen. And this is one demonstration of how initially geometric deep learning becomes relevant. In the middle, you see actually a similar figure, but now the arrows appear on the blue trapezoids rather than the edges. So the term edge, I'm sure, is so common that probably nearly everyone has heard of it. The term face might be a little less familiar, but in fact, when we say face, you can think in this example of the blue trapezoids. And it is the case that in some applications, you might want to attach data to faces rather than edges. Now, this is where topology starts appearing, because to put it very loosely, topology is all about holes, in a sense. And you can think of these blue trapezoids as being holes in this visual representation. And a final example, computer vision example, let's say, you might actually have a figure and you might endow a mesh on top of it. So in this case, we have a mesh which represents a horse, and the mesh consists of edges and also faces, polygonal faces, which arise by connecting different edges together. And as you can see, we can color code the different edges or polygonal faces with different colors which represent different parts of the horse. So in this visualization, this is an example of mesh classification, where we try to identify, let's say, predict what is the color for each edge or for each polygonal face. So now let's see a couple more examples where you might actually have a physical structure where data naturally live on graphs or on higher order domains. On the left-hand side, we have a visualization of particle interactions in fluid dynamics. So in this setup, the nodes represent positions of particles, the edges represent particle interactions, and we can also introduce a so-called message passing mechanism that allows us to understand what are the particle-to-particle interactions. So essentially what I'm trying to say with the leftmost representation here is that a natural physical phenomenon in which graphs initially are important is fluid dynamics, where you can encode information about the position of particles and their interactions through nodes and edges. Now let's look at the right-hand side figure where we can talk about higher order domains. So in this setup, this is just a clock. And what we want to emphasize is springs and self-collision in clothes. So this is a higher order domain. Why? Because now nodes, and I refer to these orange nodes, represent position of, let's say, particles in the cloth. Edges, which you can think of them as being springs actually in terms of physical interpretation, are represented by this purple spring. So now the question is, why would I want to think of edges to start with in this setup? Well, because you might have some data that have to do with tension and compression forces, and you might be able actually to attach this data to edges. And then, if you think of these squares, more generally polygonal faces, represented by the blue color, these are also very important because they capture the local geometry of the cloth. For example, you can think of just moving around the cloth or stretching it, deforming it in many ways. And using the faces, you can actually capture this information because you can have some data that represent this physical state of the cloth through the polygonal faces, and then you can attach this data to the polygonal faces. So another motivational slide to try and demonstrate how topology is important is this one, which is about learning the shape of the data. So let me try to walk you through this slide. Initially, on the leftmost figure, we just have a graph. There's no higher order information. I know that I've been deliberately vague with the term higher order domain. This will become more concrete in subsequent slides. The purpose of these initial slides is just to pictorially stimulate interest and also explain at a high level what I mean. So in this graph, essentially you have nodes represented by these orange colored circles, and then you connect nodes through purple edges, pink edges. So now you can think that you might want to group together different nodes connected via edges. There are many different ways to do that, and in fact you can think of existing well-known algorithms that do that, not necessarily in a graph setup. For example, k-means, we tend to group together different entities. So the second figure demonstrates exactly this. We introduce now a new structure, these blue colored cells, that simply depict groups of nodes. And what you can do next with this middle figure is that you can abstract away the information. You can now forget of nodes and edges, and you can simply focus on the new blue cells that you introduce and capture higher order relations. So you can see that in a sense, you start with the initial structure and you go towards some higher order structure, which means that you abstract away the details and you focus on the overall shape of the structure of the data. I know that I'm also vague in terms of what is the structure of the data. We will talk about this also later. And the reason I like this slide particularly is because it demonstrates that when you want to reason about data, you might want to do that with different levels of granularity. To use another term, we might actually care about micro or microscopic features, or we might care about multi-scale modeling, meaning that we might have information encoded and attached to nodes or edges, but this might be the case that we might be interested on just zooming out and looking at the data related to these clusters of nodes. So in the fourth figure, you can think that I repeat the process in an iterative fashion. So now I regroup, and by that I mean I introduce even a higher order cell represented by green color, and now instead of grouping together directly the original nodes, I do that indirectly by grouping together groups, blue colored groups of nodes. So in a sense, there is a hierarchical sequence now of relations, of higher order relations, and essentially I zoom out more and more. And again, once I've done that, I can only keep, for example, the cursor graph, forgetting about the blue higher order cells, keeping only the even higher order cells, the green ones. So the main point here is that we can use topology to traverse data and their shape. Now, this is a slide which is motivated more from a computational point of view, trying to make a point. So let's say that I have a graph on the left-hand side consisting of orange nodes and pink edges. And let's say that I want to communicate some information, data, from the black edge to, from the black node to the red node. The question is, how can I do this efficiently? I can find an edge path, and in fact I can try to find the shortest edge path connecting black to red. However, that might be a relatively long path to traverse. However, if you try to think about this visually, I can have a higher order structure, a blue cell, that is associated with the original graph, abstracting away some of the details, and now essentially I can pass the information from black to red through a single step related to this blue cell. So essentially, if you focus on the cursor graph, you don't need to go through all the details. You can have a higher order representation encoded through a matrix, for example, which tells you directly how you can pass information from the black to the red node. Okay, so I think this was all about motivating the role of topology in deep learning. And in fact, it wasn't just about topology. It was motivational in terms of showing how graphs are also relevant. And I'm sure for the latter, I didn't need to try a lot to convince you because you've seen graphs permeating the literature. So now I'm going to talk a little bit about different types of relations, again pictorially, because before I formalize it. So let's say that I have this original graph in the middle, and I want to identify different types of higher order relations. So to the left, you see that one type of relations consists of faces. So basically you can think of this blue square and the blue triangle. These are faces. Another way to introduce higher order relations is actually to traverse the graph. So on the right-hand side, I can use an one-hop neighborhood. For example, if you start from here, you can jump once, twice, and now you have a blue cell describing a whole path in the graph. Similarly, if you start from these nodes and if you hop twice, this will give you another blue cell, another higher order relation. Of course, then the question is, which relation is best? This is problem dependent, there is no unique answer. And in fact, as you will see, we can formalize this idea of trying to identify different higher order relations through the notion of neighborhood, which is very common in topology. And towards this point now, let's say that I have a set of entities initially represented by nodes, and I care about finding now what is a neighborhood of the red node. There are many different ways indeed, and to define the neighborhood of the red node, and in this slide I demonstrate 4 of them. One way is to simply pick all the edges depicted in yellow that are adjacent to the red node via an edge. So to pick all the yellow nodes that are adjacent to the red node via an edge. And that makes up a neighborhood. Or you can simply pick a bigger distance, not just 1 step, but 2 steps. So now you will pick all the yellow nodes that are a distance of at most 2. So the edge path that connects the red to its yellow node is a path of length 2. So this is, in that sense, a bigger neighborhood. And you include all nodes, including the ones a distance of length 1 or 2, so at most 2, let's say here. That's why it's a bigger superset. Or, if you start thinking in terms of topology now, what I called holes earlier, you can identify the yellow neighbors nodes of the red node by looking at incident triangles. For example, this is one blue triangle that is incident, and this is another one, so we picked this way the 4 yellow nodes. Or instead of triangles, you could pick trapezoids to identify what is a yellow neighborhood. So what you need then, overall, is a function that decides for every element entity in S, what is its neighborhood. There is a typo here. This should be power set of S, because the neighborhood function attaches to every entity X, you can think of it as a node in S, a set of subsets of S. So that's why I said it's a P of S. For example, you can think that for a single node, you can identify a set of edges or a set of polygonal faces, and that would make up a neighborhood defined formally by a neighborhood function. Okay, so fine. We can then formalize what we mean by neighborhood using the definition of a neighborhood function. The next question is, are there different characteristics of relations? Can we classify relations into different types based on their traits? And one way to do this is to think of hierarchical and set-type relations. So let me elaborate on what I mean by this. Firstly, informally. So again, let's say that I have a set S of entities. If I connect them with edges, that would make up a graph. We call the orange nodes as rank 0 cells, the pink edges as rank 1 cells. But now we can also add rank 2 cells, for example, a triangle. And then we end up with an enriched version of the original graph, which also has faces, these blue faces. And that can be a simplicial complex formally or a cell complex. What's interesting is that in simplicial and cell complexes, you have hierarchical relations. What do I mean now by hierarchical? Let's start making this formal. I mean that so notice here that I classified the different cells, that is, nodes, edges, and trapezoids, more generally faces, in the topological structure domain according to the rank of each cell. So essentially this implies that now there is another function, a rank function, that assigns to every entity, be it a node, an edge, or face, a number which we call it rank of the cell. So when we say hierarchical relations, we mean, first of all, that there are relations among the original entities, these nodes, and these relations are ordered through their rank. For example, in the simplicial complex, a pink edge is a relation of rank 1. And this pink edge is essentially also, you can think of it, as a group of 2 nodes. The start and the end nodes, or if it's a directed graph, or simply the boundary, the 2 nodes that are connected through the edge. on the other hand, if you think of this triangle, this basically connects three nodes. So in this case now, we said that this is a rank 2 cell, which means that this blue face, this triangle, has higher rank than any of the edges, for example, in its boundary. So that's what we mean by hierarchical relations here, that we basically rank the relations through the rank. There is another type of relation, though, set-type relations, which appear in hypergraphs. And in hypergraphs, you have a very loose structure in the sense that you don't even define a rank function so that you have the notion of hierarchy. So what do you do in that case? You simply and arbitrarily group together different nodes. So you can have arbitrary subsets of nodes making up these pink cells, let's say. But you don't care about, let's say, the cardinality or more generally the rank of these cells. Okay, so far then in this slide I try to exemplify, visualize and explain what we mean by hierarchical and set-type relations. And the distinguishing feature between the two is the presence or the absence of a rank function that allows us to rank different cells in the underlying structure. What is interesting now is that if we think for a moment of simplicial and sen complexes, they are useful. They have actually been used in practice a lot, both in applications and more broadly in topological deep learning, but they come with some restrictions. For example, the simplicial complex, if we were to look at its definitions, requires that all sub-relations of our relations belong to the complex. For example, if you think of this blue face, this triangle, then it's necessary that all the sub-relations, that is, for example, the boundary, the pink edges, as well as all the nodes, also make up the simplicial complex, are included in the simplicial complex. Why is that restrictive? Well, it's restrictive because if you think of it now from a data science point of view, this means that you have a massive structure. So if you want to define a learning algorithm on top of it, you might have to deal either with a problem of having to have an abundance of data, big data, or if that's not possible, you might have lots of missing data. And in this latter case, you have a very sparse structure, and we know that sparsity is a challenge in terms of learning. As for cell complexes, they also impose a similar complexity issue in terms of size, because the boundary of each cell in a cell complex must also be in the cell. So this is just for the purposes of demonstration that we can easily formalize all this. We just need a rank function that goes from a topological domain to the non-negative integers. And perhaps what is very important in this definition is that we have some notion of order. So if you have then two cells x and y in the structure, for example, nodes and edges. Let's say you have a set of nodes x and a set of edges y. Then you need to ensure that the rank of x is less than or equal to rank of y. And that's what I mean here by order-preserving rank function. As for type relations, in a sense, is conceptually the opposite, because we don't imply the existence of any relation in the domain. And at the end of this slide, I just repeat that a rank function induces hierarchies of relations. Simplicial sen complexes are equipped with rank functions, and therefore are characterized by hierarchical relations, whereas hypergraphs are equipped with set-type relations. So where is the gap in this? Actually reads literature and a set of topological domains. So let's just then revise for a moment what we've said. We have initially just a set of entities. Then if we also include edges, then we build up essentially a graph. And then we talked about simplicial and cell complexes, which are topological domains with higher-order relations. And we also mentioned set-type relations. In fact, we mentioned hypergraphs that are equipped with set-type relations. But what if we are in a situation again that we don't want all this level of granularity, having to populate the whole structure, every single aspect of it with data? What if we want to be more efficient? So there is a sweet spot here where we start talking about combinatorial complexes. And in this Venn diagram representation, you can think of a combinatorial complex being a hybrid between domains with hierarchical relations and domains with set-type relations. What do I mean by this? I mean we can be a little bit more flexible now, and we can allow ourselves sometimes to rank cells and some other times to not care about ranking cells. So how can you achieve this? You can do that indirectly. The rank function is always there, but we can exploit in the previous slide the order preserving relation, and in fact, specifically the fact that we have not just strictly less than, but less than or equal to. So essentially, you can think at a high level of the idea here, which is to specifically assign a rank of interest to cells for which rank matters in the application, in the underlying application. But you can, let's say, ditch all the other cells into a bigger bucket where you use the same rank, you assign essentially the same rank to this bigger subgroup. This way, since the rank is the same, the rank doesn't matter. This is just a summary where I'm trying to say that there are different traits, features of relations. So we mentioned hierarchy of relations, set-type relations. One thing I haven't mentioned is the relation between the rank function and the cardinality of a set. So in general, for example, in simplicial complexes and in cell complexes and hypergraphs, although strictly I have to be careful because I told you there is no rank in hypergraphs. So from that point of view, to be consistent with the lecture, I shouldn't have this stick here. Anyhow, the point I was trying to make is that the rank function doesn't need to be faithful with respect to cardinality for some topological domains such as cell complexes and combinatorial complexes, briefly CCs. So basically this means that you can assign a number, a rank, to each cell that is not dependent on the actual size in terms of number of elements in that cell. You can allow this extra flexibility in the definition. So then that brings us to the definition of combinatorial complex, which generalizes the previous domains, hypergraphs, cell complexes, and simplicial complexes. And now, all you need in this definition is a set of entities and also a rank function. As I mentioned before, the rank function is always there, but we can silence it through this equality in the order preserving relation. Basically, as I said, putting together in a corner the cells for which the cell and the order doesn't matter, the rank doesn't matter in the application. So let's see now some example of CCs which further elucidate the formal definition. So on the left-hand side, let's look at figure A. We have then three different types of entities, let's say. So we have in yellow zero rank cells, and these are denoted by S0, S1, and S2. And sorry, these are the yellow ones, the nodes. Then in pink, you have a cell of rank 1, and this, you can think of this simply as an edge. And finally, you have a blue cell of rank 2. And that blue cell, in this case, you can think of it as a triangle, as a face, right? Okay, now let's look at figure B. In this case, we still have three different types, yellow, pink, and blue relations. But let's look at the blue cells for a moment. So, for example, look at the top cell, which connects in total 3 yellow nodes. And then look at the bottom cell, blue cell which connects 4 yellow nodes. So in this case, what I'm trying to say through this visualization is the point that I emphasized in the previous slide, that is, rank does not imply cardinality. So, for example, the top cell, blue cell, has 3 elements, 3 nodes, whereas the bottom cell has 4 nodes. But there is no problem with the definition as it stands for the CC. We can still assign the same rank, let's say 2, to both of these cells. Of course, one question would be, why would I want to do this? Why would I want to ignore the cardinality? Well, again, that always is application dependent. You can think of it as a merit of the definition that gives you this extra flexibility. That's fine. I don't think I need to spend more time in the rest of the examples. I think these 2 examples make the point. Maybe actually it's important to make the last point here, which reinforces once more that cardinality can be ignored if desired. Because, for example, according to the ranking mentioned in the first line, in figure C, we have a CC of rank 3 associated with a green cell, whereas in the rightmost figure, we have a CC of dimension 2. So what I'm trying to say is that although in the rightmost figure you have a blue cell consisting of 6 nodes, you can define the CC to be of dimension 2 smaller than the dimension of CC C, where the dimension is 3, despite the fact that the biggest cell, in terms of cardinality, the green cell, has... you had a question? You're referring to this figure, and you refer to the blue cells. So, in this case, what you're doing essentially, you can think of it this way, is to identify different neighborhoods. For example, you could have a neighborhood for this cell, and the neighborhood in this case is visualized by the blue cell. How you would formalize that? You would need to actually formally define the neighborhood function that sends every node to the blue cell. Does that answer the question? And of course now, if on top of this, you also add a rank function that tells you what is the rank of each of the blue cells, then you have hierarchical relations, because you give, for example, higher ranking to the blue cells compared to the pink edges. But if you don't use a rank function, then yes, you're right, you just have set-type relations that would make up a hypergraph, you're right. So, fine, we have a definition of CCs. We saw some example of CCs to demonstrate the definition. How can we operate in that space now? How can we navigate the space of CCs? Towards this end now, we introduce a notion of CC homomorphism. So, essentially, a CC homomorphism allows you to pass from one CC to another. But when you make that passage, you want to do it by respective certain properties, which are outlined in this definition. So, let's say then that I have a function f, and you see that briefly, instead of denoting the CC as a whole, including the initial set of entities, the set of relations and the rank function, more briefly, I denote it by calligraphical x1, referring to just the relations. This is just a notational short. So, I have a function f that passes from one CC to another, and I want this function to satisfy 2 conditions. The first one is that if you have 2 cells, x and y, let's say 2 relations, to put it this way, from the first C, such that x is a subset of y, you want to make sure that f of x is a subset of f of y, which means basically f of x is now an element in x2. It's a relation in the other CC. So essentially you want to preserve the order here, that if you have relations that are ordered in a certain way in the first CC, when you map them through function f, you preserve that order passing to another CC. And so this is a first restriction that has to do with the x1 and x2, and a second restriction has to do with the rank function. So here what happens is that if x is a relation in the first CC, then you want the rank of that relation with respect to the first CC to be larger or equal to the relation, to the rank of f of x, that is the relation that maps x to f, the second CC. So you want this second rank related to the second CC in order to be bigger than the rank in the first CC. So what does that mean here? It simply means that if you pass from one CC to another, apart from respecting this homomorphism relation, you want to make sure that you contain the ranking, that you don't increase the rank function, the values of the rank function, so that this explodes. So let's look at an example now. So let's say that this is S1, consisting of nodes 1, 2, 3, 4, and S2 consisting of nodes A, B, C. So you don't see all the elements of the definition here, it's just a demonstration. So apart from S1 and S2 being visualized, you will also visualize calligraphical X1 and X2 through orange, pink, and blue. But then let's see, basically what I'm trying to say is that this visualization focuses in the first condition of the C homomorphism definition. So let's see then how this condition holds. For example, if you take node 1 here, which is a subset of 1 to 3, then you want f of 1 to be less than or equal, to be a subset of f1 to 3. So f1 is A in the second CC, this node. So we map this node to this node. And then this purple cell, 1 to 3, is mapped to this purple cell, AB. So f of 1 to 3 is AB, and obviously A is a subset of AB. That's what we mean here by referring to the fact that f of x is a subset of y. So now the next couple of slides are about demonstrating why we bothered in the first place defining C homomorphisms, how they become useful. The first obvious use is that we can relate the world of CCs to the big universe of existing structures, that is graphs and other topological domains such as cell complexes. So essentially, to put it simpler, we can use CC homomorphisms, and specifically a subclass of CC homomorphisms called CC embeddings, to map existing domains to CCs. So for example, you can take a graph, we can enrich it now by adding extra cells, blue cells, and we can end up with a CC. Similarly, we can start with a cell complex and we can add even higher order green cells, and we can end up again with a CC. So essentially, you can think of this process as a process of enriching existing structures, and you might want to do that if you have additional data for the higher order relations in order to land in a CC. And the reason this becomes useful is because obviously if you have now a space of CCs and you want to traverse that space and do inference later on, you would need to be able to start from well-established structures such as graphs or cell complexes and land in CCs, so that existing tools are applicable ultimately to the substructures that we already have. Now, there is also the opposite operation. Rather than enriching a structure so that you end up with a CC to work with it, you might actually want to cast away some information. You might want to simplify the structure and work in a more efficient or in a simpler setup. Can you formalize this notion? Yes, because you can define now the notion of sub-combinatorial complex. So a sub-combinatorial complex, in short, sub-CC, is also a CC itself, but essentially, at high level, it's a CC that is contained in a larger CC. So you want basically to take a CC and slice part of it, and then end up with another CC to make sure that it is well defined. So the way to do this is to take the initial rank function for the original CC and then restrict it to the set of relations in the smaller CC, and that will give you a well-defined rank function, and more generally a well-defined smaller CC, which consists of some entities, relations between them, and this restriction, this newer, simpler, let's say, rank function. So just an example of how this might work. This is again a CC, and in fact I explicitly write down all the relations in the CC here. So you can see that you have essentially 3 nodes, S0, S1, and S2. Then you have this edge S1, S2, and then you have this triangle S1, S0, S1, S2. So now, let's say that I want to focus only on that part. So that is, my set A here, capital A, consists of nodes S0 and S1. So now, if I follow this procedure according to the definition, I will end up with a new set of relations that essentially constitute S0, S1 that are included in A, and also any other relations between S0 and S1 that were originally in the first CC. So that is basically the purple edge. So through this process, I threw away the blue cell here, so that I can go again back to a simple abstraction. So maybe this is a natural point to wrap up and think for a moment what we've said so far. We try to motivate why graphs and more generally higher order relations, higher order domains, topological domains are useful in practice. And we did that by looking at specific examples of data that are supported in higher domains, of physical phenomena that are related to higher domains, of message passing that can make computation potentially more efficient by looking at curves and representations of the original graph. We then talked about 2 different types of relations. That is, hierarchical relations based on rank functions and set-type relations. And we distinguish between 2 main classes of domains based on these types of relations. Cells, simplicial complexes from the existing literature versus hypergraphs. And then we try to unify both by introducing a new domain, the so-called CC, combinatorial complex, that essentially allows some flexibility when to take into account the ranking of cells and when not. And finally, we also added some functions, for example, CC homomorphisms, CC embeddings, and also restrictions of ranking functions, so that we can pass from one CC to another, either by enriching existing structures or by removing information from them. And also, maybe I need to emphasize how important is the notion of neighborhood function that pretty much ties together topology with graphs and deep learning. And this will become also clearer later on. So, okay, one might say that so far the discussion has been abstract, trying both to motivate the discussion but also to introduce the necessary terminology and tools. But then the question becomes, okay, how about computing? How do we now pass from all these structures to encoding information for these structures in a way that is amenable to computing, essentially? So we can define a CC neighborhood function, which is also abstract, that assigns to every sub-CC of a CC a non-empty collection of sets that come from the relations in the sub-CC. But now, again, how can I actually encode that in the computer? The way you can do that is by passing from a function to a matrix. So we need now a definition for a CC neighborhood matrix. So let's say then that I have a neighborhood function, a CC neighborhood function, and let's say that I consider 2 collections, calligraphical Y and calligraphical Z, of cells in the CC. So now the question becomes how the cells in these 2 collections of cells relate to one another, and how can I encode this information? Maybe to bring up an analog, you know, for example, the notion of adjacency matrix related to graphs that tells you whether two nodes are adjacent to each other. You can think of the CC neighborhood matrix in a similar fashion because the CC neighborhood matrix in this setup is a matrix that has cardinality of Z times cardinality of Y elements, so cardinality of Z rows and cardinality of Y columns. And essentially the ij cell in this matrix has a value of 1 if the ith element cell in this collection Z of cells belongs to the neighborhood of yj. So you see now how the indices ij related to rows and columns have to do with elements zi and yj from the two collections of cells. And then, just to get back to the values that these cells take, this is just a binary matrix, so the cells take value 0 or 1. So if zi belongs to the neighborhood of yj, then the value of the ij cell is 1. Hence the similarity to the notion of adjacency matrix. Otherwise, if cell zi is not in the neighborhood of yj, the value is 0. So essentially, if you think about it conceptually, the CC neighborhood matrix simply tells you whether two cells from two different collections of cells in the CC are adjacent to each other with respect to a neighborhood function. Of course, I have to be very careful because there is formally a notion of adjacency, co-adjacency, and incidence. So we don't even need to talk about this because we can simply talk about neighborhood functions here. So the key statement in this definition of neighborhood matrix is that I belongs to the neighborhood of yj. And you can see now, of course, that the value that this matrix takes depends on calligraphical n, the choice of neighborhood function. So if you think of this more from an applied point of view now, obviously the choice of the user, the choice of neighborhood function by the user affects the computations here. This is just a high-level remark. Continuous versus discrete neighborhoods, just to bring about two different paradigms. So if you are in a continuous space, this can be a sphere, for example, you can define a continuous neighborhood function, and this would be more related to the tools from differential geometry. On the contrary, here we talk about a set S of entities, nodes, for example, that, let's say, could be living in a sphere. And then we induce some structure. For example, we can connect the nodes to edges, and then we have purple edges, we have polygonal, blue polygonal faces, and we can also rank all these different relations having a CC. And then we can also define the neighborhood function on this CC. So now the neighborhood function is not continuous as it was in the previous setup. It's discrete. It can consist of different relations, or if you want to think of it simply this way, it can consist of different subsets of nodes. And in this case, the tools that we can borrow to try to develop learning algorithms come from algebraic topology rather than differential geometry. So there is this distinction between continuous and discrete domains, and therefore between differential geometry and algebraic topology. So I would say that I'm really going very slowly. So probably we won't have a break as I was planning. So it's interesting because minus this coming part of the talk, which is about 6-7 slides, I gave the same talk in 45 minutes, so probably I relaxed too much thinking that I have 1.5 hours, and that's the result now. But that's okay, hopefully it has been more informative and easier to follow. So now I'm going to give a couple of examples to try to demonstrate how we can encode the different structures and more specifically relations that are encountered and in topological domains. And the example, the working example that we will go through over the next slides is this one. So this example is essentially a simplicial complex. It consists of a vertex set, 0 ranked cells, 1, 2, 3, 4, 5, the nodes essentially, an edge set, which are all the edges, So far this is just a graph, but now let's also think of this face set 2, 3, 4, 5. So 2, 3, 4 and 2, 4, 5. So look at these two red triangles. So this is the extra information that makes the original graph a simplicial complex. So taking together the vertex, edge, and face set, that makes up all the simplices in a simplicial complex. And all these simplices essentially together collectively make up the simplicial complex. So let's try now to try and exemplify a little bit the matrices that we use in practice. And I want to clarify that these matrices are not about the data science aspect of things yet, because we haven't populated the structure of data. This is about actually encoding the different types of relations in the simplicial complex in a computer using matrices. So we will start with a rank 1 incidence 5 by 7 matrix. So the vertex, the node set, consists of 5 nodes. That's why we have 5 rows, 1, 2, 3, 4, 5. These are the edges. These are the nodes. And then we have 7 columns which represent the different edges in the graph. So this is almost like an incidence matrix. And the reason, this is almost like an adjacency matrix. And the reason I'm saying this is because zeros and ones indicate whether there is incidence between vertices and edges. So let's take a specific example to make it clear. So let's take then first row, first column. So 1, 2, and 1. So indeed, node 1 is incident to edge 1, 2 here, and hence it is non-zero. I will explain the sign in a moment. So essentially, if a node is not attached, is not incident to an edge, then the value is 0 in this matrix. Otherwise, it is 1, let's say. Now, the reason that you see that we have both 1s and -1s is that we also take into account orientation in some sense here. This is a convention of how to define the orientation. The way we do it, for example, here, is that in this edge 1, 2, let's say there is a lexicographic order, first of all, in this representation. You can see 1, 2, 3, 4, 5, and 1, 2, 1, 3, 2, 3, etc. So we have ordered in a very specific way the rows and the columns in the matrix, just to mention this. So, and the reason I'm saying this is because initially I was going to say the starting node, but there's no start and end node here for edge 1, 2. We don't have a directed graph. But exactly because we have ordered the rows and the columns, you can say that this is a pair related to edge 1, 2, and 1 is a start one. So in that case, if it's a start node, it's -1. Whereas if you look, for example, at 2, 5, 5 is an end node, so it's a +1. But that's not the main point of the orientation. I don't want to get lost too much in the details. The main point is 0 versus non-zero, which has to do with whether a specific node in the graph is incident to an edge. So you can see the notation that I call this matrix beta B01, and 01 refers to the fact that I'm talking about incidence between rank 0 cells, that is nodes, and rank 1 cells, that is edges. Now in this case, the matrix is a 7 by 2 matrix, and I denote it by B12 because this is incidence between rank 1 cells, that is edges, and rank 2 cells, that is triangles, red triangles, the faces. So again, let's look at an example. So let's look at the triangle 2, 3, 4. Again, there is lexicographic order in the way that we represent rows and columns. So for 2, 3, 4, we can say that 1, 2 is not adjacent. It's not incident, actually. So it's not in the boundary of this triangle, because 1, 2 is up here, hence the value 0. Whereas, for example, 2, 3, which is this edge here, is in the boundary of the red triangle, hence the 1. Now again, plus and -1 has to do with orientation, so we assume that we traverse this triangle according to its lexicographic order, 2, 3, 4. And for example, if you do that, you can also attach orientation to edges. You need to do that as well. So 2, 3, 3, 4, and 4, 2. So then, no, sorry, 2, 3, 3, 4, and 2, 4. So the orientation in the edges is always from smaller values no to higher values no. So now when you traverse the triangle, the orientation of the edge 2, 3 is the same as the orientation of in the triangle. So this is why here it's a +1. Let's look at the opposite example. So 2, 3, 4, and 2, 4. So when you traverse the 4, you go in that direction, downwards. Whereas when you traverse the triangle, you go 2, 3, 4, so from 4 to 2. So this -1 shows this disagreement in orientation, essentially. So this matrix encodes both incidence of edges in relation to faces. Yeah. So, yes, that's a good question. So, formally, this comes from a definition of how we end up defining Laplacians and Hodge Laplacians. But let's say that you need to do computing somehow to start with. So, we could say let's ignore altogether the lexicographic order. But then, if you do it in an entirely arbitrary fashion, how can I possibly define uniquely the matrices and later on also do algebra with them? So that's the first limitation, that you truly need this order to be able to do computing. But on top of it, if you encode all the information and you have actually ordered pretty much everything, why not include this extra information that you have in your domain, which is also about, it's kind of, I agree with you, it's a natural question to ask me. This is artificial information. On top of all these structures, now I started adding some lexicographic order. But since I have this order there, it makes sense to try to also encode this information ultimately. It's, let's say, a natural thing to do. You could ask, of course, what happens if I ignore this information? What if I keep the order to define well the matrix, but have always +1s? I would suspect, and I haven't done the experiment, that probably that might degrade potentially performance, but I don't know is the honest answer if that's the case. So now we can also define what is called a rank 1 Laplacian. How do I do that? So first of all, let's see what that means. So this is edge to incident, faces to incident edges. So basically, I know that sounds confusing. What this says is, if I take two edges, are they incident to each other? But I define now the incident with respect to faces. So if I take this edge and this edge, are they incident to each other with respect to red triangles? Yes, because there is a red triangle that has both of them as part of their boundary. Whereas if you take that edge up here and that edge down here, obviously there's no triangle in the simplicial complex that connects them. And the value here would, inside this Laplacian matrix would be 0. So let's start with a diagonal. For example, look at 2, 4, which is this edge up here. So in the diagonal you see a 2 here because there are essentially two incident faces. So you can think of the diagonal as counting how many faces are incident to each of the respective edges. And then you can think of the non-diagonal elements as encoding whether two edges are incident with respect to the faces, the red triangle that we have here. And again, there is an element of orientation, but I'll have, unfortunately, to skip that detail. Actually, I have to tell you this, because otherwise the next slide won't make sense. So, if you take 2, 3, 4, this red triangle where we said how we traverse it, then it's 2, 3. With this notation, I refer to the boundary of the triangle. So that's the edge 2, 3, plus 3, 4. And then because I go from 4 to 2, I have minus 2, 4. So once you write down this relation, then look for example, at 2, 3, and okay, let's look at 2, 3, and 3, 4. So with respect to that boundary, they have the same sign. But 2, 3, and 2, 4, which is this one, it's a -1. because in this equation they have opposite sign. That's one way if you want to decipher. I know I said that quite quickly. I hope it was clear. But basically, you can look at the boundary of each phase, and you can use that information to ultimately decide on the sign here. But instead of doing all that manually and thinking about it, there is a much more convenient way to do it, because you can use computer algebra, and you can simply write this one-to-one Laplacian, which tells you how different edges are related to one another with respect to faces, by looking at what we defined earlier to be the rank 2 incidence 7×2 matrix, which tells you how faces and edges are related to one another. So a simple matrix multiplication will give you the up Laplacian. Now, for the down Laplacian, you look again at incidence between edges, but now instead of doing it with respect to the red triangles, you look at incidence with respect to nodes. So you decide if two edges are incident to one another based on nodes, not faces. So if you think about conceptual now about the definitions and the terms, they make sense. Up Laplacian, for example, you determine whether two edges are adjacent by looking upwards to higher order cells, that is triangles. Down Laplacian, although you still look at connection incidence between edges, now you make the decision as to whether two edges are incident based on lower order cells, that is nodes, not triangles, faces. So you can then encode the down Laplacian as well, and you can also write it in computer algebra. And ultimately, there is something called Hodge Laplacian that puts together all the information, aggregates all the information that we have for the incidence of edges by adding the down and up Laplacian. That's what the Hodge Laplacian is. So the reason I went through these slides a bit quickly is because I want to demonstrate that actually it's quite easy in terms of computer algebra to encode the structure of a topological domain and therefore to be ready to do computation. One question lingering there is, why would I bother having matrices representing the structure? I really hope I will remember to answer this question, because there is an easy answer to this. Yes, I will, because it's the next part of the presentation. So, this is a very important part, and I'm happy that I still have time to talk about it. So, look at this figure for a moment. Here, this could be just a mesh where you have nodes, you have edges connecting the nodes, and you also have triangles, faces. So you could use incidence matrices, you could use Laplacians, Hodge Laplacians to represent the structure and how different relations are related to one another, how nodes and edges and faces are related to one another. You can encode the structure. But how can we now do some learning? To do that, we need data. And basically what we need is to attach data to different elements in the topological domain. So what I do in this figure is to try and visualize this process of attaching data. So formally, there is a definition for doing this, which has to do with the notion of K cochain space. And essentially, the K cochain space is just, you can think of it as a mechanism that attaches to each cell and some information, some data. So, for example, if you take the yellow nodes, so that's zero-rank cells, nodes, vertices, then you can attach to them, let's say, three-dimensional vectors. And they're represented here by literally this yellow three-dimensional vectors. So now you can think of the zero cochain map of the zero cochain mapping nodes to these vectors. That's how I literally and formally define the process of attaching data to nodes. But I can repeat the process for higher order cells. So for example, for one-rank cells, that is blue edges, I can now attach vectors in R2, the blue vectors. And finally, for a face, a purple face, which is a two-rank cell, a triangle, I can also have a two-cochain that maps the triangle to a vector, a purple vector here in R4. So this is how I populate my structure with data. But this is not enough. once we have populated the data, we also need a mechanism to communicate information across so that we can actually learn from the data. And for this reason, we also need what is called cochain maps. So you can think of cochain maps as being a mechanism that passes around information, that data that have been attached to different ranks, that is, to different cells of different ranks. So you can see here, for example, that one way to do that is to implicate incident matrices and let's say a cochain. So let me pause for a moment because I know I started going with 100 miles per hour. So the incidence matrix is what we took the time to define earlier formally as a matrix that tells you how different cells are connected, are incident or not, to one another. So basically what I'm trying to say is that this part is not about data, it's about the structure itself and how different cells in the structure are related to one another. You can think of this HK as a cochain which attaches to these cells different data. And then if you do the product between the structure at high level and the actual data, then this will bring about a new feature vector which lives on cells of a different rank. So essentially, to bring it all together, we start with the topological domain, we populate it with data through cochains, and then we also add cochain maps to pass information across different cells, that is, cells of different ranks. So now we have everything we need to do what is called message passing. And in fact, message passing is literally pretty much everything you need in order to do deep learning and define learning algorithms on top of these mechanisms. So in this visualization, what I'm trying to say is that message passing actually on combinatorial complexes encapsulates a number of operations actually. And formally, it's not just message passing. We introduce, and I won't discuss this today, the so-called push-forward operations, which include message passing, pulling, and unpulling. So just to focus on this visualization for a moment, I have then a CC, and you see for purple cells, I have attached data to them. And then I can use a message passing scheme so that I can communicate these feature vectors across different purple relations, across different edges, let's say here. But this is not all. I might as well want to communicate information between cells of different ranks. And in this case, I might perform a non-pooling operation and go from data in edges to data in nodes, or I can perform a pooling operation and go from purple data in edges to blue data in triangles, let's say, or higher order cells. So let me say something which is very important, and I hope to come back. I need to talk about this slide for a moment, because I need to distinguish between pooling and unpooling more concretely. So what do we mean by these terms? So if you start from a set of entities and you want to pool some information, what that means is that you pass information from lower to higher order cells. So essentially you end up passing information from the nodes to this higher order, for example, green cells, or there can be intermediate steps. You can pass information to edges, blue cells, green cells. Whereas unpooling is the opposite operation conceptually. So I will start from a coarser structure, high-level representation of the data, for example, green cells, and I will pass data now to cells of lower rank. So essentially, I pass data of coarser data, or data living in a coarser domain, to data living in a more granular domain when I do unpooling. Okay. So I guess I need to leave some time for questions, right? Yeah, so let me try to wrap it up. I will then cherry pick 3 points before I close up the discussion, because I simply won't make it to the end to discuss everything. So there is obviously, it's important to mention that there is an implementation of all these structures, combinatorial complex CCNNs, that is combinatorial complex neural networks, and the message passing mechanism. And in fact, we have an open coding challenge in ICML 2023. People contribute, for example, different topological neural networks by adding pull requests. And another important thing to mention, well, that slide, is that you don't need to look necessarily at all the details of the domain and the message passing. You can kind of zoom out again using a so-called tensor diagram, which is something introduced. And basically you can suppress some of the information but still retain the overall structure of the neural network. One motivation for wanting to do this is because you might actually want to reason about neural architecture sets. Yes, I also wanted to answer a question that I asked to myself earlier, why incidence matrices, for example, matter in Laplacians, which I kind of answered here. And when I try to explain that if you combine matrices that represent the structure of the domain with feature vectors that have to do with ranks of a certain cell, then you can pass to data features related to cells of different ranks. So another one last minute, just I need to spend another 1 minute literally to mention that we have tried to test this framework based on CCNNs on different applications, including mesh segmentation, which is about identifying the level of different edges, for example, in this application. This is another mesh segmentation datasets where you can try to identify parts of an object. And we have also tried to use the framework in a setup of mesh and point cloud classification, where now you don't necessarily care about the label of every single edge, for instance, but actually about classifying the object as a whole. And we also try to use a framework on certain graph structures. And overall, without now having the time to go into details, it did have at least as good performance. But what is interesting is that by having this unified framework based on CCNNs and push-forward operations on top of CCNNs, you do manage to encapsulate mathematically, but also in terms of performance, different domains of applications under this single framework. And perhaps I want to close up by saying, why would we bother having all these enriched representations and not stick with GNNs? Well, the answer to this is yes, it is possible to start with a topological domain and find a graph representation of it, what is called a Hasse graph. However, the operations that you perform on a Hasse graph in terms of deep learning are not the same in terms of are not the same as the operations that you perform on top of a topological domain. So the topological domain is structured in such a way that respects some certain permutation invariances that are not respected when you try to do learning on a graph. And in fact, population studies, not only theoretical arguments, we did see in certain setups that if you simplify the learning process by using a graph instead of a topological domain, you do lose in some cases in terms of predictive performance. I think I'll stop here.
Thank you. Are there any questions?
Hello. Yes. Thank you so much. It was very interesting, actually. The question I have, I don't know if it's the right one or not, but let's say you gave that example of classification of the chairs or something like that, right? Which are represented as 3D, I don't know, point clouds. So I guess if it's a classification, then we get a classification score, like a probability in the end. And the question is, if you're using these CCNNs, are they invariant to rotations and translations in space? Because if you rotate this chair, it's still a chair, right? So whether the output score will be the same, is it a part of the CCNNs or not?
So The answer is it depends. It depends on how you define the CCNNs. So, for example, what we have found empirically from an engineering point of view is that if you throw an arbitrary CCNN to a certain application, it doesn't mean that it will work necessarily. It requires to handcraft it a bit in terms of picking the neighborhood functions, in terms of picking the pooling and pooling operations, which are crucial in terms of predictive performance as well. So the answer is, subject to these choices, you have indeed certain equivariances that are respected. What are these certain equivariances? That's quite a long discussion. I would actually have to point you to the paper. But yes, overall, we have an understanding of what are the equivariances that are respected as a function of the push-forward operations that you use, essentially.
Thank you.
There was another question.
Yeah, hi, thank you. Oh, sorry. Yeah, so I just want to ask, like, so do you, how do you basically decide on the structure before you start your network? So do you have any decisions that you have to make, like, before?
Yes, and in fact, it's not a new problem. To give you one example of, so once we finished this line of work, which we thought of it more from a foundational topological point of view, the next question is, can we really make now a case that this works in applications that matter? And one problem that came up is related to proteins and protein interactions. We know, for example, that there is a lot of success as well in terms of AlphaFold, in terms of identifying the shape of proteins. And with some of the collaborators, co-authors from IBM, we are trying now to identify what is the right CC that we need to define in order to get good predictive performance. So to give you a little bit of an example of how that might work in practice, then you have to answer questions such as not just what are my neighborhood functions, but more important, which defines the relations, but more importantly, what is the ranking that I have to use? Because, for example, in terms of protein, you might have van der Waals forces, you have strong or weaker forces, and maybe, for example, you can use the notion of a rank to encode that information. Or maybe you could attach data related to position of certain elements in the protein related to nodes. So yes, there is a lot of, it's not a trivial issue. In fact, you have to also work with domain experts to tell you what are the features that truly matter in the application, and you want to make sure that you capture through the rank, the choice of rank and neighborhood functions. So yes, it's not a trivial task to define meaningfully, let's say, the domain that is the most appropriate for a certain application.
So would there be a possibility of, like, kind of going up and down between, like, rank and no rank, like hypergraphs, and, like, between, like, basically, like, considering something as just like an edge in a hypergraph, and then suddenly we consider some rank?
Yes,
so, like,
I see what you mean. So, two answers to this. So, this also relates to the problem of model selection or neural architecture search. And in fact, this comes from, it's in the appendix of our work, from topological vanity theory, where basically what you can do is to define a functor that maps, let's say, certain simplified graphs, trivalent graphs, to tensor diagrams that are essentially CCNNs. Why would you want to do that? Because you abstract away more and more the details, and then within that coarse space, you can start thinking which are the relations that matter. So that's a first thought that we have of how you can start automating the process of picking the relations that will be included in the CC. But I don't want to hide away from your question, because I honestly think that it's not necessarily that simple, especially if I don't have a use case of showing that this kind of automation that we have in mind works. I'm suspicious that you probably need a domain expert to give you a little bit of guidance on what matters and what you should include in the domain.
Thank you.
Thank you. I think we have time for perhaps one more question.
Hiya, I was just wondering about applications here and also just sort of speed of things. Like, are we is there models of, say, like email to the NHS and organizational structure? Is it more of like protein folding or like other multi-omic applications? Or like, I know with the mesh of the body, is that like, sensors or like motion capture on that? And yeah, like how fast is it? Also, like, what levels of data, can I do it with hundreds of thousands of people? If so, where are we getting hundreds of thousands of labeled data points with topological information?
So,
yeah, just applications in general, and
starting from the examples in the paper, I must say there were all toy examples in terms of scalability, because essentially the data sets in terms of number of nodes and edges were very small. Now, the problem of scalability is a very big one, not only in topological deep learning, but even in graph neural networks to start with. We know that if you have massive networks, this is an extremely difficult problem to solve. And in fact, you also have to look at the features of that massive network, if it's sparse or dense, and then pick different tools to try to attack the problem. But beyond this, so the point I was trying to make is that this is an open problem. The answer is we don't have immediately the tools to scale this, but what I can tell you is that at least these initial examples, we could still run them on a laptop. There is also potential to speed up the computations, because a lot of this message passing can happen in parallel or even asynchronously at some level. So there is definitely scope for speeding up the computations. I must say one of the biggest bottlenecks in terms of computing is actually populating initially the CC, or actually building up the structure, because for that rank function to be well defined automatically, rather than having a user inputting manually, for example, thousands of edges if it's a massive network, you need to go through all the possible relations and make sure that the ranking is order preserving. And this slows down the initial phase of setting up the combinatorial complex. But even that, there is scope to expedite it, actually. One of the co-authors is working mainly on that.
Is there like a, where is the first like use in practice going to be, do you think, or is it still too early to generate something?
Yeah, sure. So what I would say is that setting aside the co-authors that focus mainly on the coding challenge, as a team, our main focus is exactly your question, and it relates to this problem related to protein structure. That's where we are trying to focus. And I guess to make the case that this all makes sense and it's useful, you would really need to showcase through this application that this extra information related to the topological domain has added value in comparison to a simpler graph. And that's the main focus, actually, in the way that we're trying to define the CC for that application. This is work in progress at the moment.
Thank you.
Okay, let's thank Theo again for his amazing talk.